La tercera comunicación tiene por título Análisis del coste energético y del ciclo de vida económico del uso de tejas de cemento fabricadas con residuos de PET en la rehabilitación de viviendas sociales en climas cálidos mediterráneos. En la comunicación compartirán con nosotros, en la investigación que están haciendo, datos que comparan el flujo energético anual que atraviesa una cubierta en una vivienda arquetípica del parque de vivienda social con el flujo anual resultante tras la intervención mediante el uso de tejas con el PET incorporado en su fabricación. Es una comunicación virtual que tenemos.
Good afternoon. My name is Helena Dominguez Torres. I'm from the Facultad de Ciencias Económicas y Empresariales de la Universidad de Sevilla. My co-author is Carlos Antonio Domínguez Torres de la Escuela Técnica Superior de Arquitectura de la Universidad de Sevilla. I'm going to present the presentation entitled Energy and Economic Life Cycle Cost Analysis of the Use of Cement Roof Tiles Manufacture Incorporating Peat Waste in the Retrofitting of Social Housing in Hot Mediterranean Climates. So let's move on to the introduction. Despite the growing interest of the industry and the support of institutions, the recycling rate of various types of plastics is still low worldwide. Thus, with respect to peat, polyethylene terephthalate, in a recent report from the organization Zero Waste Europe, it was concluded that only about 23% of all peat sold on the European market is recycled. Thus, it can be stated that 77% of the peat sold is not reused, which inevitably leads to heat storage in landfills, incineration, dispersing nature, and in general generating a serious public health and environmental problem. And according to the same report, the percentage of recycling increases to 50% for the recycling of peat from bottles, but it is only about 28% for peat from packaging trays. In large part, this low recycling rate is due to the cascade effect that makes peat, as it is reused, less interesting for use in the most common applications, mainly the manufacture of new packaging, due to the loss of its initial properties of purity and transparency, among others. This creates opportunities for recycled peat of low quality at the end of the recycling cascade to be used in other fields such as construction, where the material doesn't need to meet the high quality standards required for packaging. By using these lower grade peat fractions, the construction industry can contribute to extending the circular life of the material. And thanks to its durability, moisture resistance, and lightweight, peat is an environmentally friendly option for creating insulation materials, wall panels, roofing, and other construction applications. This utilization in construction not only makes it possible to recover peat fractions that do not meet demand and food standards, but also contribute to reducing the sector environmental footprint, promoting the circular economy, and reducing dependence on virgin raw materials. In short, worldwide, among the various types of solid waste generated in large quantities in today's society, peat has a remarkable potential in the circular economy for recycling and reuse. And owing to all the reasons outlined above, many research efforts in recent years have concentrated on using peat in construction materials. A recent work by Callejas et al. Examined the replacement of 15% of the sand mass with peat in the production of cement tiles. The study evaluated the thermal properties of the tile obtained and established that the mechanical properties of the final product were adequate for roofing applications. So what are the goals of the present paper? The first one is to assess the energy efficiency of using cement roof tiles made with peat waste in the retrofitting of social housing roofs in a warm Mediterranean climate. For this purpose, the study compares the annual energy transfer through the roof of a standard social housing unit, typical of those built in southern Spain in the mid-20th century, before and after being retrofitted with these peat-based tiles. The second objective is to perform a life cycle cost analysis of the proposed tiles over their useful life, in order to determine whether this retrofitting strategy is economically viable, comparing the total cost, operational maintenance, and installation for the retrofitted case with analogous cost of the modified reference dwelling. The case study analyzed here is a dwelling within a social housing development known as El Plantinar, located in the city of Seville, southern Spain. Built in the 1960s, as were many other similar developments in the city. These dwellings are characterized by a poor and outdated thermal envelope, leaving them highly vulnerable to weather conditions. And the buildings feature flat roofs of equal height, ensuring that no building casts shadows on the other roofs. The dwelling under study is located on the top floor, directly exposed to heat transmission through the roof, with a total floor area of 60 air per square meter. According to data from the Spanish State Meteorological Agency, Seville experiences an average annual temperature of 19.2 degrees. During July and August, the average high temperatures can reach up to 40 degrees, while in January, the average low dips to 5.7 degrees. Consequently, winters are relatively mild, while summers are notably hot and dry, with high levels of sunlight. The maximum daily average value of normal incident solar radiation occurs in July at 8.3 kilowatt hours per square meter, with the lowest average of 2.3 kilowatt hours per square meter recorded in December. The climate of the region is classified as Mediterranean under the Copenhagen climate classification, and in this study it was used the Sevilla Weather File from the Energy Plus climate file database. The retrofit proposal consists of replacing the original roof tiles with cement tiles with peat flakes incorporated, and following Callejas et al., the tile manufacturing process includes peat flakes sized between 0.15 and 2.36 millimeters with a specific mass of 1.33 grams per cubic meter. The peat replaces 15% of the sand by mass, effectively substituting that fraction of sand in the production process. And the thermal and optical property of the tiles with peat are specified in this table. And according to the mechanical analysis performed by Callejas et al., concrete roof tiles incorporating peat meet the standard mechanical property requirements for roofing applications. The energy analysis is thus based on the following items. The indoor zone under the roof was considered as a test zone. Indoor air temperature was modeled as a single value. Natural ventilation of 1 air changes per hour is considered if outdoor air temperatures are suitable. An infiltration rate of 0.3 air changes per hour is considered according to previous research focused on social housing in southern Spain. And the building was modeled using Energy Plus. Hourly heat flux was computed for a typical year from the Sevilla weather file, and hourly heat flux was computed for the reference case and the retrofitted case. The life cycle cost analysis methodology is based on the method P1, P2 introduced by Duffy and Beckham. And to perform this analysis, the following inputs are considered: the cost of energy, the performance of the equipment used for air conditioning, the initial cost of application of materials, the maintenance cost, as well as the economic variables that drove the economic process, the increase of energy cost I, and the monetary discount rate D. Regarding the lifestyle of the tiles with peat incorporating, the study by Almosevi and Navas concluded that with an adequate proportion of peat, less than 30%, replacing sand, the tiles with peat incorporated meet long-term strength standards similar to traditional concrete. Therefore, in the present study, we took an average value of 40 years of service life for the considered concrete tiles with incorporated peat. So, if P sub E, C and P sub E, I, H are the current prices of energy for cooling and heating, respectively, the present worth of any future energy payment C sub E of chi in the period chi is given by this expression, where C sub E of chi is given by this expression. Being SEER and ECOP, the seasonal energy efficiency ratio for cooling and heating, respectively, of the equipment used for conditioning, while Q sub C of chi and Q sub H of chi are the cooling and heating loads of year chi. Then, for a lifetime of 40 years, the present worth of energy cost for the whole life cycle, total lifetime, is given by this expression. So the present worth of the life cycle total cost per unit area of the roof surface is given by this expression, where C sub I is the cost of the initial investment of installing the constructed solution considered, and C sub M are the cost of maintenance for the entire time period. In order to calculate the difference between the use of the retrofit and the reference cases, the net savings for the whole life cycle period is calculated as follows, where C sub T ref and C sub T are the present worth of the life cycle total cost per unit area of the reference roof surface and the retrofitted roof case, respectively. Then, if net savings are larger than 0, then there are positive or real economic savings. The variables considered to perform the economic calculations involved in the life cycle cost analysis are listed in this table, and all variables included in the table have been obtained by averaging values found in specialized literature, manufacturers, Eurostat, and engineers' construction price generator. So moving on to the results from the energy analysis, this figure shows the monthly heating and cooling loads for the reference case and the case retrofitted with cement tiles mixed with peat for a typical year in the city of Seville. As can be seen in the figure, loads in the cold months are higher from the retrofitted case, while in the warm month it is just the opposite. This may be due to the higher solar reflectivity that peat tiles exhibit compared to the reference roof service, owing mainly to the presence of peat plates. This figure and the table below show the yearly total load for the reference case and the case renovated with cement tiles mixed with peat. As can be seen in the figure and in the table, the renovated case has a lower annual load. Although the reduction achieved is not very high, 2.62%, the fact that energy consumption is reduced, together with the removal of peat from the environment, contributes to a reduction in greenhouse gas emissions and environmental pollution from plastics. And regarding moving on to the economic analysis, two scenarios have been considered for the economic analysis. S1, the retrofitting of the reference case is carried out for energy and environmental reasons and not because the reference case needs retrofitting, and S2, the reference case needs to be retrofitted. In this case, two options are considered: repeat the initial system or retrofit the roof with cement tiles that incorporated peat. For the analysis, it has been assumed that the home is conditioned using a heat pump with an average efficiency of EER equal to 4.5 and SCOP equal to 3.5, corresponding to mid-rate equipment. In cases 2, the estimated manufacturing and installation price according to CPA Engineers construction price generator for ceramic tiles is equal to 38 euros per square meter. As described above, the life cycle cost analysis has been carried out using the P1, P2 method. This table shows the results obtained from the life cycle cost analysis. All values are in euros per square meter, and as can be seen in the table, for scenarios 1, the total cost for the entire service life are 360.3 euros per square meter for the reference case and 396.65 for the retrofitted case. Therefore, in this case, there is no real economic savings in total cost over the entire life cycle. This is because the savings in energy consumption costs achieved by the proposed retrofit measure are not sufficient to offset the cost of the measure if this is carried out solely for the purpose of improving energy and environmental performance without the renovation being necessary due to the state of the original building's roof. So, as per scenarios 2, that is assuming that the roof needs to be renovated and installation costs are unavoidable, the total cost for the entire service life are equal to 398.3 euros per square meter for the reference case and 396.65 for the retrofitted case. So there is a slight net saving of 1.65 euros per square meter. This saving does not seem significant enough to justify the proposed retrofitting. In purely economic terms, the proposed retrofitting produces a very slight saving. However, considering that this saving is linked to a reduction in energy consumption and the removal of a significant amount of peat from the environment, it can be considered that the proposed renovation offers sufficient advantages to be interesting from an environmental point of view, as it reduces greenhouse gas emissions and the release of substances harmful to the environment without incurring additional cost. So, conclusions. This study investigates in the first stage the energy efficiency of roofs when using cement tiles manufactured by adding peat waste to retrofit social housing roofs in a warm Mediterranean climate such as that of southern Spain. To this end, the study analyzed the annual energy transfer through the roof of a typical social housing unit common in southern Spain in the mid-20th century before and after being retrofitted for a typical climate year in the city of Seville, Spain, where the case study was conducted. The energy analysis shows a slight decrease in the thermal loads of 2.62% for the retrofitted case compared to the reference case. So in a second stage, a life cycle cost analysis is performed to assess the economic feasibility of the proposed retrofit, and for this purpose, the P1, P2 method was used. As a result of this cost analysis, it was concluded that the retrofitting of the roof of the social housing in consideration using the proposed solution is only profitable in purely economic terms if the roof needs to be retrofitted, and the question is what type of retrofitting is carried out. In this case, retrofitting with cement tiles incorporating peat results in a net saving of 1.65 euros per square meter
for the entire life cycle time period considered. Therefore, it can be said that this type of renovation, when compared to the use of other more conventional materials, results in a small economic savings that make it economically viable. However, the strongest points in favor of using this material for the renovation of social housing are decrease in energy consumption and therefore reduction in greenhouse gas emissions, and use of a material with little prospect of reuse and therefore reduction in associated waste and the corresponding environmental impact, all of which are in line with the Sustainable Development Goals of the 2030 Agenda. Thank you very much for your attention.